This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. Hope you have received the template of the DSO. How many of you have not seen the template on LMS? Okay, good that you all received it. So today in the first lecture I will discuss about the front end of the DSO, how to design the front end up to ADC. And in the second lecture I will discuss about the anti-aliasing filter, data converters, because both are important, because now you got the template. Again I will be discussing about the DSO remaining block level diagrams in the coming lectures. So you have got plenty of time, and then until last year we did not teach all these block levels, but then we decided to teach block level diagrams. So you are lucky because we are teaching you all the block level diagrams. So then the one of the main aims of this subject is you should be understanding how to design a system, or when there is a requirement how to design the system. So we will be studying through that DSO, but then the initial thinking, like you should be learning how to think, because that is very important. For example, when do you need a microcontroller? For all the designs you don't need a microcontroller. And then when do you need a microcontroller? And then when you don't need a microcontroller. For example, someone asked you to design a circuit, measure the temperature of this room, and if it is more than say 30 degrees, just light up a LED light. That is a requirement. So design a simple circuit that will measure the temperature of this room, and then one LED will light up, red LED, if the temperature is above 30. Then you don't need a microcontroller. Obviously you can do with a microcontroller, but then for this one you don't need a microcontroller. Why? So this is a requirement. Immediately you heard, then you have to be thinking, okay, I have to measure the temperature of the room, then I have to light up the LED. Then you already got one component. So you got the component, one requirement is one red LED. So that you already got. LED, that is red. So that is you got the LED. Sorry, I think I'll get a new paper. Yeah, so then you already understood you need a red LED. Then you have to measure the temperature of the room. Then you should be thinking, okay, so some sensor is required. So you need some temperature sensor. Then you will be writing, okay, so then you will be drawing, or you can draw the block level, or this is one block. Then second block is you need a sensor to measure the temperature. Then, okay, temperature sensor. Then temperature sensor you got it. Then you can't connect the temperature sensor to the LED. because then it is not going to work. Then you got the temperature sensor, you need LED, but then you will be drawing, okay, I got a temperature sensor, this is a temperature sensor, then you need something here, and then that will be connecting to this red LED. So that's how you should be thinking. Then what is the middle part? As I said, you don't need a microcontroller. Obviously, you can design with a microcontroller, but this is a simple system. So you should be always thinking in a simplistic way. Then you add up the complexity based on the requirements. Because you will see some of the designs, electronic designs, where they use components unnecessarily, unwanted logic, but then you can cut short those. Especially, for example, in space-borne systems, like because I come from aerospace background, they always check your design. It should be redundant design, because complex designs will fail. Because for doing some particular thing, even in the DSO, I can show you some examples. Today I got 2 examples, the design front end. Some students design in a particular way, some students design in a particular way. Same things you can design in so many ways. So the elegant and simple solution always prevail, that will not fail. More complexity, more failure rate. So in aerospace, basically they will review your design and find out whether that logic is good. So that is the reason in some car companies, why their parts are failing. Some car companies, maybe Toyota got a very good reputation, their parts are not failing, their technology is good. But then you can also start a car company, you can get the same kind of design. Why it is failing? Because some particular way of design will fail, because that is a bit more complex, or that is not maybe ideal when you connect it. So it is a very challenging. So the electronics also, when you design, it should be simple design. You should start from simple, elegant design, then you should increase the complexity in the system design. Especially that is relevant when you go for mass production. Some companies, they will check your design, and then they may say that, okay, mass production, this is not good, expensive. So you may have to redesign it, which we have done in the past. Then something you need here, then for this particular one, you don't need a microcontroller. Temperature sensor, then you need something that make a decision. And then here LED, then you will be connecting some power supply. Maybe you have connected 5 volt, then you need some signal when it is exceeding 30 degrees, because that is our 30 degrees is our cutoff. Then you need something that will give a signal when temperature is above 30 degrees. That's how you should be thinking. Then here it will help in doing so. Then you may think that, okay, here maybe I can use, maybe if you have studied a comparator, you can simply use a comparator, and then you can use a comparator. In the comparator, what you are doing is here maybe you connect 1 volt, and then here you are connecting your red LED. And then from the comparator, when you connect your temperature sensor, then here you got a power supply, and then you are grounding. But then this temperature sensor output may be voltage, small voltage, then you need some amplification. Then you need an amplifier. Then if you find a lot of noise, obviously no noise. If noise is there, you will be adding one more block filter. If not, if there is no noise, you don't need a filter. So temperature sensor, you are getting some voltage. Most of the time with sensor, you need an amplifier, because the voltage detected is small. Then you amplify accordingly, and then you have to test it. Maybe when 30 degrees come, then you can adjust this amplifier. When 30 degrees is sensed, you can, the amplification here should be maybe 1.1 volt. When 30 degrees comes. So then you can tune this amplifier. So 30 degrees, then you will change the gain here, and then say 1.1 volt, this output, that is Y. And then this is the temperature, like you will be making a graph. 25.8 volt, that you will find out. Then you will say, okay, I'll put 1 volt here in the comparator. When it is 25 volt, 25 degrees centigrade, this will become 0.8 volt. In that case, what will happen is your positive is 0.8, excuse me, negative is 1 volt. This is a comparator, and if this is grounded, and then if it is 5 volt, when the negative is more, this will be 0 volt. So when the temperature is less than 30, 25 degrees, this is off. But when the temperature is 30, this voltage shoot up to 1.1 volt. Then what will happen is here 1.1, here is 1, so this will shoot up to 5 volt, and then this ready will be on. See, this is a simple system, and you don't need a microcontroller. But then when do you need a microcontroller? So firstly, this is how you should be thinking. You may be drawing the major blocks. Whenever you hear a problem, you will be drawing some major blocks logically, and then you will be trying to connect it. Okay, this is an input to this block, this is output. So this block does something. Then you have to think. Then you have to break up the block. Oh, here I have to do two functions. So maybe I need two blocks there. Excuse me. So that's how you should be doing. Then, so this is a simple case. Then somebody said, no, this system is good, but I want to open the door for 10 minutes when the temperature is exceeding 30 degrees. You know what I meant? And then the door should stay there for 10 minutes. Then all the people can go out and then close the door. Then also the requirement is also there is a specification. You want to adjust how long the door will be kept open. Maybe 10 minutes, maybe in some cases 20 minutes. You know what I meant? In that case, then then you have to write a program, because some program needs to be written. The door should be open for 10 minutes. That is X some time that you can input. Then you need a microcontroller. Then you will what you will do is then maybe your system design will be different. You have got temperature sensor, then you got amplifier, and then you are getting the amplifier input. The soon you introduce microcontroller, you need digital signals, because microcontroller, RAM, all these things, we need digital signals. So far, here if you look at it, you don't have any digital component, except here you can say 0 to 5 volt, maybe kind of a digital, but actually it is not digital signal. Here you are getting some temperature signal, and then that is varying, there is a comparator, and then that is going to LED. Soon after you get amplifier, soon after you have microcontroller, you have digital signal. So then you need ADC. Then, so now you have to make some decisions. Then you have a microcontroller. Then microcontroller, this amplifier input, that is analog. You cannot connect analog input to the microcontroller. You need digital signal. Then you will be having amplifier. Then you have ADC, because you have to convert your analog signal to digital. Then you go to microcontroller. In the microcontroller, what is microcontroller? Then here one pin will be going. That may be connecting to a motor or something, and then that motor will motor will connect it to the door. You're taking a decision. You know what I meant? Then in the code here, you write the code. Okay, keep the code you can write. Keep the door open for 10 minutes. After that, close the loop, and then that's when the temperature is sensed 30 degrees. So the microcontroller will be reading the temperature, and then it is opening the door. See, when you are doing something, and then when you have to make some decisions, like doing so many things, then you need to write a program. Then you have to use a microcontroller. So microcontroller is kind of a brain. When you have a complex system, that is a brain that is doing all the executions. For example, again I am going to increase the complexity. Also, I will be here this microcontroller. Then I am going to give. So this is got a temperature. Then it is saying you also take into account humidity. Then humidity, some values, they say 70%. Then you are making another. So not only temperature, when humidity is 70%, when the temperature is exceeding 30, then only you make a decision. Then only you open the door. Not only with the temperature. Again, you have to make some kind of comparison. Who will do comparison for you? So then in that cases, you need a microcontroller. You will be writing the program. So when you have microcontroller, as a system engineer, you know that, oh, I need ADC before that, because it's a digital. So that's how you should be realizing the blocks. Maybe you got an idea of designing simple systems. Now we'll go to the DSO. So in the DSO also, I will teach you how to think. Suppose DSO, you never worked with the DSO. How many of you, by the way, didn't work with the DSO? I know that somebody sleeping, they might say yes. Check, find out who is sleeping. Definitely you worked with the DSO, ECD. That's the reason the prerequisite is ECD, so that nobody will say that I never heard of DSO, because you already used the DSO. So suppose that DSO is not invented. and then you joined in a company, very promising startup. They are going to develop a DSO, and then they will say that our requirement is measuring some voltage and then display on the screen. So that is a requirement. Then you would say that, oh, measure the voltage and then display on the screen. In the previous example, the screen should be, maybe they will say that the easy way is display on your laptop, because maybe we will start with displaying on your laptop. Later we can develop an inbuilt display. So when you want to interface to computer, we will go back to the previous case. So here we got a temperature sensor, humidity sensor. You want to open the door, but at the same time you want to connect all the data, you want to connect to the computer, and then you may have to plot it, something like that. So this is your desktop or your laptop. So immediately when you connect to the laptop, then you need some communication protocol, because when you want to connect your laptop to the system, your PCB microcontroller, then you need some kind of communication protocol. So that's why we use a communication protocol like I2C, or some people say I2C, SPI, TXRX. We will study those. And then if you don't have laptop, then you don't have to worry about this communication protocol. So if you want to connect your laptop or anything to the system microcontroller, then you need a communication protocol. That's the reason we need a communication protocol. So now you know, as a design engineer, you know how to write down the blocks. Whenever you hear the problem, you will be writing down, you will be drawing the blocks, major blocks. Then when you think, again you will split up those blocks depending upon the specification. When you are using a microcontroller, you know you need ADC. When you want to connect some laptop or something, you need some communication protocol. So these are the basic things you should be knowing as a system engineer. Now we will go to the DSO. So the DSO, somebody said we are making it for the first time. So the first is measure the voltage and waveform. So waveform is important. Then only you get the frequency. Second, display. So display on laptop. So that is the only requirement the company said. Then how will you design it? So how to measure the voltage waveform, how to display on the laptop. Then we will be starting the design, simple block level diagrams, how to think, how to measure the voltage. So maybe you will be touching some point. There you got some voltage. Then you need maybe a probe or something, you will be touching the voltage, and then from there your voltage is coming in. So when you have voltage here, maybe you are getting an analog voltage, something like this, a sinusoidal wave. So this is your input you are getting from somewhere, this is the ground. So this is the X point you are testing. So this voltage you want to display on the laptop. So that is the instrument you are going to design. So when you have that voltage, you cannot directly connect to your laptop. You will damage your laptop. How will you connect it? And then when you have that voltage, then you will be thinking the coarse way, not fine way. Oh, this voltage might have a different amplitude. Then maybe it's a very small voltage, so we have to amplify. Definitely you need to amplify. So then you will be having an amplifier block. Because this is a small signal, there could be noises. Then you will be thinking, okay, amplifier, maybe I need some filter. So you will be putting some low pass filter. Because low pass, high pass, band pass, which one you need it here? Because you need a low pass, because your oscilloscope should be passing all the low pass. There maybe higher cutoff is fine. You don't need a band pass. You know what I mean? Oscilloscope should measure the DC voltage. Oscilloscope measure at least some frequency. So you need a low pass filter, not a band pass filter, not a high pass filter. So you need a low pass filter. After low pass filter, what happens is you need a ADC, because you need to connect to the laptop. So then you may need a ADC. So this is a major blocks. And then after ADC you are getting the digital data. So I will make it parallel. After that, the digital data, what you will do with that digital data? Because you can't directly connect the digital data to your laptop. So you need to store somewhere. Then you may need a RAM. So that's the reason we use a RAM. So when in the system, whenever you have ADC, when you have data you have generated, then you need RAM. So in the RAM you are writing the data. But when the data is coming to the RAM, from here the voltage value here, this is analog, then here this became digital. But when the digital values are coming in the RAM, whenever you have RAM, you need a counter. So counter, C-O-U-N-T-R. So this is a counter. So what is the meaning of counter? Means it will generate address, because in the RAM, see this is a RAM. Then what will happen? Your digital data is simply coming and storing. Later it is not possible to retrieve it. So you need to store it properly with some address, some digital address. So that digital address is generated by a counter. So the counter will be storing the data, helping. So we will study this in detail later, but this is just in an end-to-end overview. So that is the reason we need a counter. Whenever you have a RAM, you need to generate some address. With respect to that address only, we store the data in the RAM. Then from the RAM, you will be connecting to a microcontroller. And then this microcontroller is that is a brain. There you write all the programs about the DSO, what you should be doing the waveform. And then when the RAM here, the data is storing, and this microcontroller, and then from here you will be connecting an interface to the laptop. So, so this is a laptop, then you will be connecting to the laptop. And then here maybe you will be using some communication protocol, maybe SPI from the microcontroller. So then this microcontroller will take the data from the RAM, and then it will give it to the laptop, and then you will generate you have to design a GUI, graphic user interface, then only you can display it. You are getting the digital data. So this is a kind of a codes representation of DSO. And then here you are just displaying using microcontroller here, then you are displaying in the laptop. But then now we will be thinking in the oscilloscope, you are getting some waveform that is converted into digital form, and then digital form you are storing in the RAM, because you need in the system a RAM for putting the data. So whenever you design a system, if you want to read it to the PC, you need a RAM, so that you are writing in the RAM, then later you can read from the RAM. And then who will do that one? You need a microcontroller for writing, and then that will control reading. And then you need a protocol, communication protocol, SPI. So here SPI, or some people use I2C, and then some protocol that will enable you to get into the laptop the data. And then you may be designing a graphic user interface where you can display the waveform. But then when it comes to oscilloscope, now this is just designing, but then here if you do like this, it will randomly displaying some waveforms. It will not be like your oscilloscope, neat waveforms are coming continuously, because here one thing is lacking, that is called a trigger function. If you don't have the trigger function, your oscilloscope, all the signals will be randomly displayed. So that is we are missing so many blocks in the oscilloscope. So we will be introducing block one by one. We need the trigger signal, and then you have to take into account the frequency of operation. If the microcontroller cannot handle the high speed, then you need something else. So that's how we will be thinking, and then we will study the DSO in detail in the coming slides. So this is how we will be thinking. So as a startup company, they set the requirement, and then you came up to here. So you know how to, low pass filter, ADC, RAM, microcontroller, laptop. At least this much is a kind of a draft skeleton. Then we will be adding more flesh on into it depending upon the requirements. And then this is a kind of, this is not the full DSO block level diagram. This is how you should be thinking. Then once you know how to think, then we can easily learn the remaining blocks. So today what I will do is I will discuss the front end of the DSO. So front end is up to here. So all these remaining blocks, plus there are more blocks. So that blocks we will be studying in the next lecture. So we will study today the front end of the DSO. So having said this one, these are the major blocks: amplifier, low pass filter, then ADC. So these are the major blocks. But then when you have oscilloscope, there are other requirements. If you see your specification, have you seen your DSO specification? Let me see if I got a copy. So we have given you a specification. So then your company will give you, whenever they develop a product, they will make a specification in the industry. So then with respect to that only, everybody will make a design. Nobody will design any product in the company without a specification. In your case, that's the reason we prepared a specification like, see, in your case, what are the specifications? The device will have one analog input. So you should have one analog input. Then I will take my sheet, a new paper. So device should have one analog input. So maybe this is my input, one pin. The input will be through a BNC connector. So yeah, then I will be having one input. So that is my BNC. Then, so this part is fine. Second part, input will have a 1 meg ohm plus or minus 10 ohm input impedance from DC to 1 kilohertz. And then, you know, our DSO, what is the cutoff frequency of our DSO? So we said the DSO, when we talk about DSO, some people say that what is the cutoff frequency, or some people will ask what is the sampling rate. Most of the time for DSO, people use the latter, sampling rate. So in your case, if you read the design specification, you have to design a DSO with a maximum sampling rate of 40 mega samples per second. 40 mega samples per second. So I will write here. So that is 40 mega samples per second. So that's most of the time they will say sampling rate. But then when you have 40 mega samples per second, by Nyquist theory, the bandwidth you can get is half of this one. So 20 megahertz. So that is the reason you will be designing your filter with 20 megahertz. So your cutoff will be around 18.5 cutoff, because ideally it should be 20, but you can't get 20, then it should be a sharp transition. So when you have sampling rate of 40 mega samples per second, you cannot get a bandwidth above the half of the sampling rate by Nyquist theory. So we will study that one in the coming slides if you haven't studied it. So then 1 meg ohm input impedance. So when you connect your signal here, it should have 1 meg ohm input impedance from DC to 10 kilohertz. So then we will connect a DC voltage and vary the frequency up to 10 kilohertz, and then we measure the impedance, and then it should be 1 meg ohm. Then below again we said another specification. The input must have an impedance between 10 kilohertz and 30 megahertz of greater than 100 ohms. So what it meant is in the DSO, see, in order to meet these two, what it says is we will plot the impedance at the input at the BNC, and then this is the impedance, and then this is the frequency, and then DC 0 volt, 0 frequency, this is the 10 kilohertz, and then maybe this is the 30 megahertz. So what it says is this is 1 meg ohm. So when you do the impedance measurement, then it should be 1 meg ohm up to 10 kilohertz. Then at least it should be greater than 100 ohms. So it may be, say you got 300 ohm, that is good, up to 330 megahertz. So you should get that one. So if you want to get something like that in the input, then you know that using a resistor alone you can't get it. So you have to think of how can you get a impedance that is depending upon the frequency. If your system got that type of specification, what element you can add? Yeah, you can add some capacitors and make some impedance network, then you can do it. Then we will do that one later. Then the input will have an input capacitance of less than or equal to 60 picofarad. So whenever you got oscilloscope, the capacitance will decide. Again, that will create a low pass filter. If you have capacitance, then you got impedance of the probe together to form a low pass capacitor. So if the capacitance is very big, you might be designing maybe say 100 megahertz oscilloscope. You have got all the ADC for that one, but because of the input capacitance, you don't get more than 20. So that because in the front end itself it is forming a low pass filter. So then this also you should be satisfied. Then BNC input can accept a maximum input of plus or minus 5.6 volt after which the input voltage is clamped. Means your BNC, so when you come to your BNC or design here, this BNC should not accept more than plus or minus 5.6 volt. Because if somebody is connecting 10 volt, you don't want your DSO damaging, or somebody connected 50 volt by mistake. Also there is another thing, when you design the DSO, we need some voltage range, because based on that only you can tune your ADC and remaining all the things. And then so we have to specify some voltage range. So our voltage range of interest is 5.6 plus or minus 5.6, because we need that range. Based on that we can make our proceeding stages, plus it's also kind of a protection. If somebody is connecting 20 volt or 30 volt, you don't want to damaging it. And then when you take this much specifications, now we got in a couple of blocks. See, first I will be reading BNC. I got the BNC connector. Device will have an analog input, and then through BNC connector. Then input will have a 1 megohm plus or minus 10 input impedance from DC to 10 kilohertz. The input must have impedance between 10 kilohertz and 30 megahertz of greater than 100 ohms. So from the BNC, then I need some block. Here the impedance should be, ZC should be a function of frequency. That block I got it. Then input will have an input capacitance of less than or equal to 60 pf. Again, this will be taken into account. Then the BNC input can accept a maximum input of plus or minus 5.6 volt, after which the input voltage is clamped. Then that should be not after this one, that should be coming here, because that is soon after this one. So then I will put, maybe here I got another block called a clamper. See, clamp, because it's called clamped, so we need a clamper block here. Then the signal path from BNC input to the ADC shall be DC coupled. So what do you mean by DC coupled? Means you should not allow to connect any capacitor in parallel like this. Means from BNC, if this is your BNC connector, and then you may have so many circuit, one block, then you have another block, then you got, your ADC may be here. Then it is not allowed to put a capacitor like this, AC coupling. You know what I meant? Means when you connect a capacitor like this in between, you are blocking the DC. Then you can't measure the DC, and also it will form a high pass filter. That's the reason it should be DC coupled. DC coupled means you should not use a capacitor in between up to the ADC, because up to the ADC is a front end, because after that you got digital, you can't connect a capacitor. So it should be DC coupled. So when you hear the term DC coupled means then you will not be using any capacitors. Then so we got these blocks based on the writing. See, when you have specification as a design engineer, you will be writing some blocks in the order and then making sense of it. Okay, this is how it will be thinking. You know, system design is a systematic approach, and then you will be thinking systematically and then writing the blocks like as I did. Then we will come to the next specification. The anti-aliasing filter appropriate to the 40 mega samples per second maximum sample rate must be implemented with a minimum of a first order 20 dB per decade response and plus or minus 2B maximum ripples in the pass band. Then what it says is you need an ADC, and then the oscilloscope should have 40 mega samples per second. And then when you implement ADC, so whenever you have ADC, people will put a low pass filter before the ADC. And then as I said, when you are dealing with the microcontroller, when you have got a microcontroller in your circuit, you need digital signal, so you need ADC. As a system engineer, you know that one. Same way, when you have ADC, always people put a low pass filter, and I will tell you why. We will study anti-aliasing filter, especially for DSO. We need anti-aliasing filter. Even for applications, people put a free because when you have 40 mega samples per second, then your Nyquist, as per Nyquist theorem, your bandwidth is around 20 megahertz, half. And then we need to stop all the signals there, frequencies. Otherwise, you will get an error. So whenever you have ADC, you need a low pass filter. So these are the things you should be remembering as a system engineer. But then here in the specification, they already said you need an ADC. Then you understood, okay, after coming here, you need an ADC. That's what he said. But then it's also said you need to implement a low pass filter with some specification, minus 20 dB per decade, first order. It said first order, but then I wouldn't recommend. At least first order it is mentioned. First order means you can put RC, then you are getting a first order. Then what is the RC pole? Minus 20 dB per decade. That is very poor. So I would recommend please don't use, because in the specification we said at least, but please don't use RC. Use op-amp, second order filter with minus 40 dB per decade. Otherwise you will struggle in the design, because your sampling is 40 mega samples per second. So I will come to that point why we need at least minus 40 dB per decade. You need a second order. Then from the specification, now we don't care about the numbers. We know when ADC is read, we need a low pass filter. Then the question is where to connect the low pass filter. Definitely not before ADC, sorry, not after the ADC. You need to connect the low pass filter here. So then from the specification, see, we came up to here. See, here what I did is nothing but just drew the specification. We need a clamber, we need some impedance, some tuning case, we need a low pass filter, but then you need a ADC. That's what we understood. Then what we will do is, but then we have plus or minus 5.6 volt, but then when we think it is starting from minus 5.6, then minus 4, minus 2, minus 1, then you may have 500 millivolt, then that voltage might be very, very small. Minus 500 millivolt, minus 250 millivolt, then 0. 0 obviously we don't need to measure 0 volt. Then you may have 100 millivolt, 200 millivolt. So you got a range. It is starting from very small value to a big value. So if it is small, what you will do? You need to amplify it. Then you have to introduce in. So from this block, then you got the idea. You need some kind of amplifier. That's the reason. So we will be adding an amplifier. So somewhere here we will add an amplifier. So we need an amplifier block. And then now we will think. So when you get to these blocks, then you will be searching for how to implement it. And then when you start searching for how to implement it, then you will find out 40 mega samples per second. You will be searching for an ADC. And then we already given you the ADC. And then when you have ADC, then you will be searching for the data sheet, and then the ADC will tell you how to connect to the ADC. When you have some analog signal, ADC manufacturer, for example, this is your this is your ADC, ADS 830. So when you look into this ADC, then you got the data sheet, because this one is 8-bit 60 megahertz sampling, or 60 megahertz you can go, but then our requirement, we are using only 40 mega samples per second. That is our requirement, but this can go up to 60 mega samples per second or 60 megahertz. Is depending upon the clock. This is a clock you can the available means this can go up to 60 megahertz clock. It will work. So or 60 mega samples per second. But then our design, we need only 40 mega samples per second. So we are not using to the full extent. And then when you use this ADC, you will be seeing here. See, in the front end you see some circuit, and then your signal should go here. But then the ADC, when they make ADC, they will say that the ADC will not accept maybe your voltage range. So when you look at in the data sheet, in the ADC they will say that standard single-ended input range, that is between 1.5 and 3.5 volt. See, the ADC will not accept 0 to 1.5 volt. So ADC, they will say that this ADC will accept maybe from 1.5 to 3.5 volt. But then your oscilloscope, you should work from minus 5.6 to plus 5.6. So what will you do? Yeah, you have to scaling circuit is required. So that's how we should be. So when you look at the data sheet, you will see more information. Oh, then we need some scaling circuit before the ADC. Then we will come back and say, oh yeah, we need to add scaling circuit. So then they will add a scaling circuit somewhere. See, one more block is needed, a scaling circuit. See, then here you need amplifier, then here a scaling circuit. Now you got 2 more blocks, you have to add it. See, this is a front end we are designing. Now we are going to design it. So now we got all these blocks. Now we will connect somewhat in a logic way. So what we will do is we got the BNC. So this is the BNC connector, and then from the BNC connector immediately we will go to the clamper. Clamper is also called so this one is scaling, means it should not be confused with this voltage scaling, or people use a name called a level shifter. So the scaling means you can do scaling different ways, because when you cut off some voltage, clamper also sometimes called voltage scaling. So that's the reason voltage scaling is important, or the more appropriate name is level shifter. Before the ADC you need to shift the level of the voltage. Maybe that is the most widely used term, level shifter. Then we got BNC, then we will be having the clamper. So clamper circuit. So clamper circuit also sometimes called scaling circuit. So that's the reason I said this scaling is different from this voltage level shifter. So better to use level shifter here, voltage level shifter. See, V level shifter means voltage level shifter before the ADC. So this one is called a clamper circuit, because we need to make sure that your voltage is always within that plus or minus 5.6 volt. After that, usually what we do is, so this is a scaling circuit or clamper circuit. Then after this scaling circuit, your BNC, you got BNC, then most of the time when you design the system, it is good to have a buffer circuit. So the advantage of buffer circuit is it is isolating whatever you connect from what is going in. So most of the time they put a buffer, so you need a buffer. So the advantage of buffer is when you connect something external, you want to make sure that the impedance values are not much affecting after that. So they connect a buffer circuit. So here we are connecting buffer after the clamping. Why? Because you don't want to burning your buffer. So if some voltage or something high voltage, somebody connected 100 volt, they don't want to connect to the buffer and burn the buffer. Buffer will damage. So that is the reason you got the clamping first, then you got the buffer, and then this buffer will isolate up to from here this part to this part in terms of impedance. So that's the reason then we will connect a buffer circuit. It's a good idea to connect a buffer circuit. So that's the reason the DSO design, you will be having BNC first, then you got a clamping circuit or a scaling circuit, then you will have a buffer, and then what you will do is you need that we will come back to this point. See here what you need: a low pass filter, LP. After low pass filter, what do you need? So we got a buffer, then we got a clamper plus, maybe I will say clamper plus scaling circuit, because here we will be doing that, because we combined these two. We combined these two into this one. So this block, because you need to cut off your voltage plus or minus 5, and then you also need the impedance you want to tune it. So that I drew it as a one block. Then it is good to have a buffer, then good to have a low pass filter. But as I said, when you have a small signal, you need kind of amplification. So that's the reason we can add one amplifier here. So after amplifier, what will happen is you have to connect to the ADC. But then before connecting to the ADC, I already said we need a voltage level shifter. And then you can connect to the ADC. So these are the major blocks of the ADC, the front end. And then now we can draw it. So now what we are going to do is, see, we got the BNC, then this is a clamper, then this is the I will call it as a scaling, because this is for the impedance. You can tune the impedance, input impedance, because what you have shown here, see. And then this is the clamper. Here you should be making sure that plus or minus 5.6 volt only is going through. Then we will be drawing all the, then we will be connecting a buffer, see, because this buffer will isolate. After buffer, we will be cutting off all the low frequency so that only the required frequency will be going through, then that only will be amplified, and then you got your voltage level shifter. Then you will be going to the ADC. So all this part, this is called front end. So front end of your DSO. So this is called the front end up to ADC. So it's easy to design and also easy to think it, because from the specification we got a BNC. From the specification we understood you need a clamper circuit that should be cutting off if anything is above 5.6 or anything is below minus 5.6. Then you need some kind of a scaling, in the sense you want to change the impedance value. So you need some kind of circuit. After that you need a buffer, because buffer is always good in any system that will isolate it. After the buffer, you have to make sure that you need a low pass filter, because you are using an ADC. That is our requirement is 40 mega samples per second. So whenever there is a cutoff frequency, we will be using a low pass filter to make sure that you don't get any error, and we will study the error in the next lecture, why we get error if you don't have low pass filter. And then after low pass filter we put an amplifier to make sure that in any system we put an amplifier, because we need to amplify to the required signal level. Then whenever there is ADC, we need a voltage level shifter, because from the amplifier output you might be getting some voltage. That range might not be acceptable to the ADC. So you need some kind of voltage level shifter. And then up to here is called the front end of DSO. And then the front end is, so that's the reason people ask, what did you design? Then people might be saying, I designed the front end of the system or front end of the sensor. So front end. So usually front end means they designed only the analog part, because front end is analog. Up to the input of the ADC is front end. And then your simulation report. In the simulation report, we will be asking to submit your simulation up to here. I will show you an example, because you can't simulate ADC. So up to here, you should be submitting the simulation report. That is your first report on LT Spice. And also I will show you what we are looking for in the simulation report. And then now we are going to come to the design. How to design, and you already saw some circuits, and now what I am going to do is I will show you an example.
So, can we clamp the LTF and amplifier together? Because we are going to use an op-amp for the second order filter, so we can use gain and use that as an amplifier.
So which one? Sorry, I didn't get your question.
So the low pass filter we will be designing using an op-amp.
Yep.
So with feedback, can we use that as an amplifier as well, or should we use a separate amplifier?
It's up to you. You can maybe design together. Amplifier and buffer, yeah. Sometimes people you can change. These are the general kind of how we design a system. But then based on his question, people implement in a different ways. Sometimes they put a buffer amplifier together, and but please don't shift the clamper, because clamper there is no point in putting after maybe after a couple of blocks, after voltage level shifter you are putting the clamper, there is no, but then scaling circuit, the impedance matching also is at the input, so you can't change from there. But other blocks, in the sense the amplifier buffer, that part you got a bit of flexibility. You can add one more inverter, or whatever the way you are designing the filter. It's again in the filter. Why don't you put gain in the filter? Yet there are so many ways you can do. Filter, you can introduce a gain, then you may not need the amplifier. But then you may need an inverting amplifier if your filter is an inverting filter. So please make sure that you can design the filter in different ways. If your filter is inverting the signal, then you have to invert back. You know what I mean? Then you need an inverting amplifier. Yeah. So this is one way of implementing, but that block you can implement different way. Having said that, before the ADC, the voltage level shifter should come. The level shifter you can't shift to anywhere. It should be before the ADC. And again, low pass filter also should be before the voltage level shifter, because you can't connect voltage low pass filter anywhere else. And otherwise this buffer amplifier, these things you have a little bit flexibility, you can tune it. And then I can show you two implementations. And anyway, good question. So one implementation is somebody, I can show you some examples. So this is a design. Well, I removed the values so that you won't get the values. So, yep. So I just, you don't need the values because anyway you are going to design it. Anyway, it's on the LMS. You can see on my lecture capture. So somebody, this is an LT SPICE simulation. Somebody did it. See, you can see. So here you will see plus or minus 5, but in your case it is plus or minus 5.6 volt. And then this resistor, I don't know whether you need it or not. When you want to do some tuning, some people connect to this resistor, otherwise it will be a straight line. See, this is your BNC. So here is your BNC signal, see, BNC. So I am going to compare with our diagram, our circuit, what we have drawn. So this is the BNC, see, this is the BNC. Yep, so now we can see. So BNC, so this is the BNC, some signal is coming, and then this is a clamper. So we will be using two diodes for this clamper. See, this is a clamper BNC. I am putting C here, so this is C. So this is a clamper circuit. So what it does is, suppose here, due to somebody connected here 10 volt, say, so if it is 10 volt here, what will happen? So here I got 10 volt, and then here I got maybe plus or minus. Yeah, so when it is 10 volt, this diode will be on, and then when this diode will be on, this is on and then shorting with whatever the 5 volt here, so that this part will never go beyond 5 volt.
No, sir, the diode will have its own voltage.
Yeah, so that is around 600 millivolt. So that is the reason we said plus or minus 5.6. So then this will be dropping 0.6 volt, and then remaining it will not, never it will become plus more than plus 5.6, and then because you got plus 5 volt. When it is 4 volt, what will happen? When it is 4 volt, this diode will be reverse biased, nothing will happen, it will go through this to here. Again, when it is minus 10 volt, somebody touched here minus 10 volt, what will happen is this diode will be on, and then it will be again shorting to this minus volt, and then here again you will have 600 millivolt drop. So this will not exceed, this point will not exceed because of two diodes, it will not exceed plus or minus 5.6 volt. If you want to change your design, you want to make it plus or minus 10.6, what will you do? Same thing, here you will be connecting plus 10 volt, minus 10 volt. So this diode clamper, so this is your clamper circuit. And then from the clamper, so you already implemented, and then from the clamper, then your next block is ZC. Because you need some kind of control over the impedance, because when with respect to frequency you need to change the impedance. So whenever you see something, you have to change your frequency with respect to impedance. Then you will be thinking, oh, the only way you can implement is better to use capacitors. Using resistor you can't. So that's the reason then we will be using. So this clamper output is connected to something like a filter RC, and then the middle part we are taking. So by varying this RC, you can get the specification. Your impedance is up to here this much, up to here this much. So that is this part. So this part is ZC. So I am just putting, so that is a ZC part. After that you are going to a buffer, and then, so that is the reason here, when you move it, here we got a buffer circuit. See, here just we use it as a buffer in this design. And then the buffer output we are going to see from the buffer. So that is a buffer, see, B. So you got the B of B. From the buffer, it is going to the second order. This is a second order filter. See, what type of filter is it? Yeah, Salon key filter. Well, you don't need to use Salon key because I presented Salon key. You can use some other multiple feedback. And then you got the Salon key filter, and then the filter output is coming. See, so this is the filter output, LP. So you are getting LP. Then after the filter, after what is a filter? After the filter, we have connected some amplifier. We need an amplifier. See, but then when we implemented the amplifier, you will see some complication, because here you got an amplifier, and then you got a voltage level shifter here. So it's kind of a combination, you can use it. Then how we decided, because after this low pass filter, you need a what are the blocks? After the low pass filter, you need amplifier, voltage level shifter, ADC. So these are the important blocks we need. But then when you see the circuit, we have designed something like this. We got some kind of amplification, then we got some kind of circuit like this combined. Then why we decided like that? It's not we decided,